Good morning, everyone. My name's Kate, and I'm a Business Development Manager in the CPD unit at Cardiff University. Really delighted to welcome you all to this session today, and thank you so much for joining us. Just to reiterate from the video there, we're going to take some questions towards the end of the session. So if you have questions as you're going through, please just use the Q&A facility at the bottom of your screen, and as I say, we'll take questions at the end. So now I'd like to introduce you to Professor Tom Blenkinsop, who's going to be taking today's session. So Tom, thank you very much.
Thanks very much, Kate, for the introduction, and I'm very pleased to be with you this morning. I want to talk this morning about the problem represented in my first slide of the requirements for the green economy from the mining industry. There is really a huge problem, which I'll try to illustrate, in going from a mine to supplying the minerals that we're going to need for transitioning into the green economy. And I want to look at that problem in a little bit more detail. By way of background, one might note that in 2019, 40% of the UK's electricity supply was from renewable energy, a figure that was barely imaginable even 5 years ago. And this sort of ramping up of green energy does create enormous problems and challenges for the mining industry. So I've broken the problems down into these 5 questions, and we'll go through more or less in that order to try and make some sort of conclusion about this huge problem. So let's start off with, what minerals do we need? Here's a periodic table which has got some of the important technologies we're going to need for the transition to the green economy from the point of view of generating new renewable energy. So, for example, fuel cells require this rather interesting group of platinum group elements for their construction. Batteries require nickel, zinc, cadmium, and lithium. Photoelectric cells, the green boxes, and turbines, the blue ones. Now, some of these metals, the base metals like iron and copper, these are quantities that we can estimate that we're going to need in vast amounts, and really, regardless of what technology is used, we're going to be needing huge amounts of these base metals in the future. But the other more exotic elements, including the specific platinum group elements and the rare earth elements, are very much more difficult to predict in terms of demand because of the phenomenon of substitution. It's possible quite often that we can substitute, particularly amongst, say, the rare earth elements down here, one for another in response to availability and demand. So it's actually very difficult for these so-called special metals to predict what exactly we're going to need. So let's move on to the question of how much we're going to need. A simple and really quite striking fact is that an electric car uses 4 times as much copper as a car with an internal combustion engine. That's a good starting point to get us thinking about what sort of increases we're going to need in metal and resource supply for the transition to the green economy. And then there's some other statistics here about concrete, aluminium, iron, copper, and glass. Probably the take-home point from this slide, though, is that basically in most minerals, and we're going to require something between a 5 and 18% annual increase in global production. That is hugely challenging for an industry like mining where there are huge lead times into gearing up production. This quote at the bottom here from a recent and rather dramatic book by David Wallace Wells says the scale of the technological transformation required dwarfs every technological revolution ever engineered in human history. I don't think that's overstating the problem, and when we think about that in connection with the minerals we're going to have to supply, we realize what the scale of this problem is. So let's move on to the next question, which is obviously following from that one. We're going to need very, very much more. How much actually do we have, and are we going to run out? This table here shows various estimates of what people think we have available to us in terms of copper. And what is most striking about this table is that the estimates vary by nearly 2 orders of magnitude. And there's a simple take-home message from this, which is that global resource estimates are very uncertain. They depend very strongly on the methodologies which are employed to obtain them. And the next slide goes into that in a little bit more detail, probably too much detail for us at the moment, but if we look simply at two basic difference between 2 methodologies which are employed to estimate the amounts of resources available to us. We can start from a geological point of view, which is basically looking at existing deposits, making some estimate of what deposits might be left to be discovered, and simply adding up all the numbers to arrive at a geological estimate for the amount of resources available. On the other hand, quite a lot of different approaches take a more economic view of the problem, and they start by looking at how production has varied in the past, how it's ramping up, and how that sort of increase might continue into the future. Often these sort of techniques fit empirical or other equations to the production curve to arrive at some sort of estimate. And because these 2 alternative methods are starting from such extremely different viewpoints, they're arriving at very different estimates for the resources. So we really do have a problem, a very fundamental problem, to know how much of any particular resource is available to us. In the next 2 slides, I'm going to show you a possible solution to that problem. Now, this is probably a periodic table as you've never seen it before, because in addition to simply showing the elements, it actually shows their ions. For example, you can see Fe3+ here and Fe2+. And like any periodic table, it's got a whole series of symbols and numbers which give you a summary of their ionic properties, as well as the elemental ones. This was devised by the very brilliant scientist Bruce Railsback. And what comes out of this periodic table is that when we think of the metals, we can divide them into different types, so-called hard, intermediate, or soft cations according to their geochemical properties. Now, the importance of that comes in the next slide. This is a graph which shows the so-called ultimate recoverable resource, what people think might be the actual final amount of any particular element that's available to us to mine. And that figure is estimated by various means that we've mentioned already, and it's plotted against the crustal abundance, well, in the upper crust, of that particular element. Now, we know these numbers, the crustal abundances, really very, very well. Some very clever geochemical studies have been done on this issue. So we know those numbers. We can estimate these numbers, and lo and behold, there's a reasonable positive correlation. In other words, the more abundant the element is in the crust, the larger its ultimate recoverable resource will be. And we can even fit a straight line to that. But there's obviously a lot of scatter, and that scatter is partly a function of geochemical properties of the elements, whether they are hard or soft cations. So the idea here is that by taking into account their geochemical properties, we can better fit this line and arrive at a more reasonable estimate of the ultimately recoverable resource, perhaps at least within an order of magnitude, rather than the 2 orders that we saw currently exists. Well, that's an interesting line of research to pursue. So let's move on now to the next question. When are we going to need these minerals? And can we in fact get them in the time frame that we're talking about? I'm going to start approaching this problem using the phenomenon of peak oil, which we're all very familiar with, following the work of M. King Hubbert in the 1950s. Hubbert predicted that production of oil in the US would rise to a peak sometime in the 60s and 70s and then fall as resources were depleted. And his prediction was remarkably accurate, except for the fact that he didn't know about and couldn't allow for the new resource, which is hydrocarbons in shale, which is shown in these red dots on the graph here. But if production had continued from conventional resources, it would have almost precisely followed the trajectory that Hubbert predicted. And that's a really interesting piece of insight, which we can take forward to the problem we're considering at the minute. Here's just a bit more detail of what he actually did. We're looking at billions of barrels of oil plotted on this axis against time on this axis. His idea was that discovery rates on a cumulative graph would increase up to some maximum value. These would be followed with a certain time interval by production. So after discovery, production is delayed by the number of years necessary to put infrastructure in. In Hubbert's case, he estimated that to be 10 years. And the difference between these 2 curves shows you how much you've got in terms of reserves at any time. So that's basically how Hubbert worked his very elegant theory of peak oil out. So let's take that and apply it to minerals. And here is one estimate for what might happen for copper in the future. And what we can see is indeed very similar to what Hubbert predicted. There will be a peak in copper production, which may occur as soon as 2040, if we simply look at the way the production has increased in the past and how it's likely to evolve in the future. That is quite a worrying figure, given how close we are to 2040 and how much copper we're going to need in the future. That's not the only such estimate which gives us this sort of concern. Here's a different estimate, more recent one, but nevertheless, peak copper production is predicted perhaps as soon as 2060 to 2080 in this model. So we're getting the feeling that time is running out to find and extract these resources. Here's another periodic table, and in this one we're looking at when peak production has been predicted for different elements in the periodic table. And what is really alarming in this study is that there are some elements, tantalum, gold, bismuth, for example, which may already have hit peak production, and many others which are going to hit peak production within the next 5 to 10 years. So this is giving us a real sense of urgency about the situation for supplying metals for the green economy. Finally, on this issue, there's another way of looking at the problem, which is called the so-called critical materials approach. And in this approach, we don't only consider the availability and the amounts that we might actually mine of any element. We look at, on this axis, the risk to supply these elements, which takes into account a lot of different factors, political, economic. And we also consider their economic importance. So gold, for example, has got a very low economic importance. It's really not used for very many industrial applications. And clearly then, in a graph where we're plotting supply risk increasing in that direction, economic importance in that direction, this part of the graph is where we should be starting to get really alarmed. And there is tungsten featuring up in this part of the graph. And then various other elements which are considered in this analysis from the EU to be in the critical category. Now, this sort of graph, this particular graph was made 3 years ago or so by the European Union Raw Materials Working Group, and the graph does change on a year-to-year basis. So we'll find that different elements fit into the critical category as things like substitution are employed to bring them into the mix. Nevertheless, it remains a great way of looking at the situation for mineral supply, and emphasizes once again that we've got a certain number of elements, including the platinum group elements that we saw before, and the light rare earth elements, which are in the critical category. Okay, now I'm going to move on to mention just a few other things about how resources and society interact within the framework of whether we have got enough time to get our minerals out of the ground. And this is a schematic diagram showing the resource cycle from the formation of an ore body through to its tectonic deformation in the earth, and then the stages which interface between the resource in the earth and society. And of course, these involve, first of all, exploration and discovery, and secondly, mining. Taking those factors into account, there's a couple of other things we need to think about. In this analysis by Ali and others in 2017, they looked at global exploration expenditure over these years. And what they found is quite an interesting sort of roughly cyclical picture, with a marked peak just after the global financial crisis, but in very more recent years, a plummeting of expenditure on resources. And of course, this has direct implications for the amount of resources that we're likely to discover in the future if this sort of trend continues. Another factor, or another way of looking rather at that same factor, is shown on this graph here, which shows the reserves that we know are in the ground that can be economically exploited against the production, which is ramping up, and particularly the ratio between what is left in what we know is left in the ground, the reserves, and the rate at which we're producing it. This grey line here is showing a very worrying downward trend. In other words, we're using up the reserves that we know about, even as we discover more and more, because the production is ramping up at such a rate. And then finally on this subject, we'll quickly look at another problem which is inherent to producing minerals from mines, which is that once a discovery has been made, as we saw from the peak oil production, peak oil scenario, there is a considerable time delay between discovery and production. And at the best, in more advanced economies, that might be as low as 13 years, but it might go up to 23 years in less advanced economies. So we can't just simply go out, discover a new resource and add it to the production. there is an important time delay to take into account there. So now I'm going to address, finally, the last question here. Can we get these minerals that we need? And this is actually the most important part of my presentation. The barriers to extracting minerals are not fundamentally to do with their discovery or the amount that are available to us, or even the time frame on which we need them, big as those problems are. What is still more important, and what is widely acknowledged in the minerals industry, is that the interfaces between mining and society are actually the determining factor which is going to govern how this whole scenario evolves in the future. And one of the most important aspects of this complex interrelationship between resources in the ground, environmental impacts and socio-economic impacts generated around mining is the fact that mining contributes the largest amount of global warming induced gases, so contributing to our current climate crisis. It is the largest single contributor. And that, of course, is a huge problem when we come to think of ramping up mining to produce metals, in other words, and in order to meet the demands of the green economy. Mining itself is a major contributor to global warming. So it's a very complex problem that we're looking at with lots and lots of different feedbacks. And in the next few slides, I want to explore a few more aspects of this relationship between mining and society. So we can, the 4 problems I'm going to look at specifically, there are many others. The most important one is this concept of social license. The social license to mine has been challenged for very many people, particularly because of bad historical practices. And we can think of terrible mine disasters such as the 2019 Brumadinho dams tailing dams failure in Brazil as one of the most recent and dramatic ones, in which 259 people were killed. So the mining industry faces this huge problem of getting social license to mine at the moment. The second one we've mentioned briefly, the environmental impacts of mining, particularly global warming, but it's not just global warming. Of course, there is the impact on water supply, soil resources, for example, and pollution. And again, we can refer to the bad practices in the past as reasons why naturally the social license to mine is very challenged. We've mentioned before that the global resource base is very poorly known. So we don't actually know how much of any particular mineral is in the ground to be exploited. And then finally, something I haven't mentioned before, but we'll briefly dwell on in a couple of slides, is the dynamism of the commodities market, which makes planning and prediction extremely difficult. Well, I can't emphasize enough the problem with the social license, so I thought I would put in this slide here. The Brumadinho dam failure, taken just a few days after the failure and the consequent devastating loss of lives in Brazil, dramatically revealed by this spread of the red tailings dams from the iron ore mine across the landscape. And of course, here in South Wales, we're no stranger to this sort of terrible problem with this dramatic picture of the Aberfan disaster looking in some ways remarkably similar. I'll mention quickly now that issue of the volatility of the commodities market, which is illustrated on this left-hand graph according to various measures of how copper price is measured over that period of time in the last century. And I'm just showing you on the right-hand side one explanation for why this graph has got such extreme fluctuations. This is the result of a very simple model which I've been working on with my colleague Owen Jones in the maths department, in which we set out to try and understand how these fluctuations might actually occur. And we created a really remarkably simple model in which we specified a number of tons of a particular hypothetical resource being discovered at a particular grade, so the red dashed line is at one grade, the black is at another grade, how it might be extracted as a function of time, and then we ran the model to investigate what effects that would have on the price. And these sorts of fluctuations that we can see in the output are really quite similar to the sorts of things we see in the real market. So what that is teaching us is something that many economists already know, which is that the feedbacks in the market for commodities are so complicated, or so strong rather, that the fluctuation in price is an inevitable consequence of that sort of nonlinear and chaotic system which is set up between demand and discovery and production. So that's something that we need to bear in mind as a sort of an inherent effect of the whole way that the supply system is set up at the moment. So I don't want to end on a totally negative note, so I'm going to refer you to this paper and a report earlier from the United Nations, in which it has been realized that the Sustainable Development Goals, the SDGs, interface very strongly with the mining industry. And there are some of the connections shown by aspects of the SDGs, such as land, water, food, energy, and materials here, which are facilitated, or a consequence of, rather, the mining industry, shown in these arrows here, which often go in both directions. Now, apart from illustrating, again, the complexity of the system around mining, what that also can be used to illustrate is that there is a possibility, if mining is done in a responsible and environmentally friendly way, that it can actually contribute to all 17 of the Sustainable Development Goals. So that's a very positive conclusion from these studies, that if we do mining to obtain the necessary resources to transition into the green economy in a responsible way, we can actually enhance the Sustainable Development Goals. So my last slide here tries to answer the questions in an abbreviated form, as you can see there. And I think fundamentally that if we realize these problems, as we do at the moment, then we're well on the way to providing solutions to them. And although it is a huge challenge to think how we're going to provide the resources we need for the transition to the green economy, we can actually get there, provided we insist on a responsible approach to mining. For me personally, as a geologist, that is a great scenario for the future. Okay, well, I've covered a lot of ground in the talk, and it would be great to have any feedback through the chat or Q&A function, and I'll try and answer as many questions as I can. Okay, I see that there is already quite a few contributions from Mariano Puchetta. Thank you, Mariano. The first point that you raise is that European Union and Britain are targeting electromobility needing batteries, particularly lithium, and social sustainability in countries where this mineral is exploited, such as Chile, Bolivia, and Argentina, are going to therefore, well, basically the idea is that there are going to be important consequences for the developing countries from which these resources are currently being extracted. Absolutely a really important point there. There is there's something which I'm sure you're familiar with, Mariana, the idea of the resource curse, the fact that developing economies often have the resources which are needed by the developed economies, and they are extracted, and the benefits from those resources don't flow back to the countries which own them. And this is at the core of this idea of responsible mining. It cannot be, any mining that does occur cannot be carried out in a way which leads to social injustice, particularly on that sort of global scale. And it's an absolutely key aspect of solving the main problem that I was talking about. Can we get these minerals? That there is a justice involved in the way that these minerals might be supplied in one place and used in another. So I think that's a really important point. You continue by asking, is it correct to speak of PV panels and wind turbines as clean energy? Well, I guess that's true. They still require some sort of they come at some sort of environmental cost. It's just a lot less than the current provision of energy, and I suppose these are our least worst form of thinking about the transition into the green economy at the moment, because of the scale on which they can provide energy. But all the same, you're right that they do still have an environmental cost. And your final question is about nuclear power. Yes, I haven't actually addressed nuclear power at all in this discussion, in this presentation. There are probably a whole suite of other problems associated with nuclear power which need addressing, and basically we didn't have time to go into that. It would be certainly a topic for a complete additional seminar. I wonder what you yourself think about the viability of nuclear power. It's certainly causing major rifts, isn't it, in the green approach to economy, green approach to the future, with some camps advocating that nuclear power is really the only option, even from a green point of view, and others vehemently against it. And of course, all of that has been put into terrible perspective by the Japanese nuclear failure following the Tohoku earthquake in 2011. Okay, those are a few quick responses to your great points, Mariana. If we could have any others. Okay, Timothy Shepherd asks, how frequently do these minerals coexist? Are many mines single product? Might there be efficiencies to be made on the back of industries such as nuclear? Okay, the first two points there that you make are really good ones. A lot to do with the viability of most mines nowadays is indeed the specific mixture of resources that they can provide, not just the single commodities. And so your question, how frequently do these minerals coexist? Almost every large mine is producing more than one commodity. And so they do occur together. That's inherent to many of the ore-forming processes that go to create these mineral deposits. But more importantly as well, the specific mixture, as I said, is what determines the viability of a mine. So in the future, as environmental consequences of mining are going to play a more and more important role in determining how and what gets mined, it is the specific mix of minerals that we're going to get in any particular deposit that is going to determine the viability of that mine. Right.
Hi, Tom. Just wanted to say thank you very much for your session. That was really most interesting, and we've had some really interesting questions come in as well. I think we've got one more comment. Are you able to take that?
Sure. So This asks, in my opinion, do I believe that the mining industry is wrongly accused by the public to be extremely harmful to the environment because it has been grouped with shortfalls and environmental disasters caused by the petroleum industry? I believe many people of the public cannot make the distinction between mining and the extraction of fossil fuels. That's a quite interesting point. Well, that I'm not sure, to be honest. You may well be right that, to use rather a bad pun, the mining industry has been tarred by the same brush as the hydrocarbon exploiting industries. And maybe it is indeed true that people view them as one general evil sort of global activity. That's actually a point I haven't thought about very much before. I would just say, though, that the mining industry itself has got its own, the minerals mining industry has got its own negative perceptions, regardless of what's happening in the hydrocarbon world, because of those terrible bad practices historically and those disasters that we mentioned. So it's already got a mountain to climb in terms of gaining social acceptance and social license, regardless of how people associate it with the hydrocarbons industry. Okay, Mariana's come back again with a specific question about thorium as a potential mineral for the green economy. Well, yes, I think this is quite an active topic at the minute. I don't really know enough about it to give you a very clear answer than that, except to say that thorium is indeed one of the ways that people are looking forward to generating nuclear energy. And it would be exciting to think that there might be ways of doing nuclear energy which are much safer and perhaps on a much smaller scale than what we conventionally think of as a nuclear reactor. Definitely one of the problems with nuclear industry is that it tends to involve these ginormous investments into specific plants. And what inherent problem there is that they take so long to construct that planning one for completion and putting into production with a time scale of 10 to 15 years means, or 20 years even, means that by the time the production is actually made, generated from the nuclear power plant, the whole scenario might have changed. So in a way, that huge lag period, the lag between planning and developing nuclear power is in itself a very strong argument against nuclear power. It's not flexible enough, in other words.
Okay, thanks very much, Tom. Oh, have we got a final question come in, perhaps? Are you okay to take a final question?
Yes, of course, yes. Will the so-called green economy resolve the current pollution problems plus global energy needs? It looks like as natural other side problems will occur. Would it not be more reasonable to curtail infant growth? Absolutely. I think that we can't look at this simple problem of transitioning into the green economy just as carrying on business as usual with some sort of renewable energy provision, because as you and others have pointed out, even providing these these renewable energy sources in itself still generates problems. So I personally think, and it does become more of a sort of personal matter, I think, when we get to this stage of the debate, that there has to be a more fundamental change in our outlook on how the world is going to develop in the future, which definitely needs to start by looking at our criteria for success. And I'm actually thinking about this quite a lot at the minute, because as we come out of the COVID lockdown period, it's interesting to see already that people are measuring the success of the economy by how much it's growing. We just see that in the news just here in the UK in the last few days. The growth of the economy is measured as, is taken as the single indicator that we're returning towards some sort of productive and ideal state. But in fact, of course, I'm sure you're right that we need to actually change that paradigm really in the future. And there's a comment from Ben Slack about developing mineral resources within Europe. Battery mineral exploration is a growing focus. And would not this be a more green source due to lower environmental and social costs? And absolutely, Ben, that's a really interesting point. And in fact, I might add that I'm involved a little bit with a project here in Wales to look for potential sources of battery minerals here in Wales, which is one of the last places that you might think of for an exploration program. So I do think that having local exploration programs, thinking about rather smaller scale production and thereby addressing the question of social justice that was raised right at the beginning is an important way forward. Of course, the barriers to that are huge. The social acceptance of mining in more developed is sort of diminishes in proportion to how economies develop. And so it's really interesting to think how we're going to overcome that if it's actually a good thing to do. Ting Ting asks, is there something like a geologist code of ethics which would direct new geologists going into the industry to choose responsible companies to work for? Would this have any effect on the industry or put pressure on companies to change their practice? That's a great question. Absolutely great question. I know that there are ethical statements embedded into many of the professional organizations for geologists, such as the Geological Society of London. They do contain ethical statements, but it's probably something that we need to do a lot more about, the idea of geoethics. And in particular, from my point of view as a university lecturer, I would like to say that it's something that we're trying to include more and more in the curriculum in a very explicit way to make sure that our graduates are aware of these largely ethical issues. So it is a growing movement, and it's something that we need to press for more and more, this ethical approach to the extractive industries. Thanks for a great question there.
Right, so we've had some really super questions there, and I think we're going to end the session now. But thank you so much, everyone, for attending. Thank you for great questions, and also thank you to you very much, Tom, for such an interesting session today. If anyone has any other questions, then feel free to get in touch with the CPD unit. Otherwise, thank you very much, and goodbye.